Every series that we've dealt with up to this point have been positive series, meaning every term in the series was a positive term and it was added to the previous term for the accumulating sum. So all the tests that we've learned up to this point were for positive series only. The nth term test for divergence, direct comparison test, limit comparison test, integral test, all those tests, p-series test, all for positive series only. Well, there's this whole subset of series where not every term is positive. Every other term or every third term or every 10th term could be negative. And so those are called alternating series. Most of the alternating series that we have, the terms alternate in sign from one to the other. I've got a couple of examples here. Here is where the first term, where n equals 1, the first term is positive, but you can see the second term, a sub 2, is negative, and the third term is positive, and the fourth term is negative, and so on. We can have the first term negative and the second term positive, but the signs, SIGN signs, alternate, and that is what is known as an alternating series. Now, a sub n can be anything. A sub n can be any of the familiar series that we know, some sort of manipulation on n where n starts at 1 unless we're told otherwise. But they're series with an alternating term. There's some term in that nth term that forces those SIGN signs to alternate between positive and negative. Here are 3 examples. Here, if I was going to generate the terms in this series, when n equals 1, 1 to the negative 1 is negative 1, so that's negative a sub 1. When n is 2, that's negative 1 squared, so that's positive, so that would be positive a sub 2. As a matter of fact, anytime n is odd, we would have a negative term, and anytime n is even, we would have a positive term. Let's generate this one. We still start at n equal 1, but it's negative 1 raised to the n plus 1. This is a case where n is 1, it would be negative 1 squared, so that first term would be positive. When n equals 2, the second term, a sub 2, we would have 2 plus 1, so that would be negative 1 cubed, which would be negative. And you can see that this one is going to alternate in the opposite way. So depending on where we start, and depending on what's happening to your alternating term, then your first term could be positive or negative. Here's another alternating term that doesn't involve negative 1 raised to a power. Now, most of the alternating series that we see, this is going to be the alternating term. It's going to be negative 1 raised to some power of n. But this will also serve as something that acts like negative 1, because we know iterations of cosine with pi are going to give us either, from the unit circle, either positive 1 at 1, 0, for 0, for 2 pi, for 4 pi, or this point over here, negative 1 at pi and 3 pi and 5 pi. So when n starts at 1, we start here at the cosine of pi. Well, the cosine of pi is negative 1, so it would be negative a sub 1. When n is 2, that's the cosine of 2 pi, so that would be positive a sub 2. When n is 3, that's the cosine of 3 pi, which would be negative a sub 3, and so forth. So that alternating term can look like anything, so kind of be on the watch for that. But when you have an alternating term, and when your signs alternate, that completely changes the sum of your series. So we're going to spend some time talking about the sums of alternating series and how we're going to find whether these series converge or diverge, because they're not acting like the positive series that we've been looking at. So here's a couple of examples. Here is the series negative 1 raised to the n plus 1 times 1 over 2 to the n. So you can see that your a sub n term is going to look like those positive series that we've been working with. So the alternating series are really just some alternating term you can look at them like this. There's some alternating term times some positive series that we've already dealt with. Now, that does change the sum because every other term is going to be added and every other term is going to be subtracted. So your sum is going to look completely different for the sum of a positive series. As a matter of fact, this series is the counterpart to the harmonic series. Can you see that a sub n in this series is the harmonic series? We know the harmonic series diverges. And it diverges, very slowly. It's smaller and smaller and smaller terms added to an accumulating sum, but it does diverge. So I wonder what happens if, since it diverges so slowly, if we subtract every other term. Does that mean this alternating harmonic series, which is what this is called, does that mean it converges or diverges? Well, we'll see here in a minute, using a good test for alternating series, what it does. But just like if we can identify the harmonic series, we get to go directly to the fact that we know it diverges. It's going to be important for us to identify and state that we know we're looking at the alternating harmonic series, and we can state what it does, either converge or diverge. So let's look at the alternating series test. This says, let a sub 1 minus a sub 2 plus a sub 3 minus a sub 4 and so on be an alternating series with the magnitude, the value, regardless of the sign in front of it, regardless of whether it's a positive or negative sign. The magnitude of the terms is getting smaller. That's what it's saying. It's saying that a sub n is bigger than a sub n plus 1. Well, there's a sub n, there's a sub n plus 1. So it's saying that as I continue to add terms, or as I continue to generate terms, and I don't care if they're positive terms or negative terms, but as I continue to generate them, those values have to get smaller. And this is important. We can't just, this is the if that we get for the then of the alternating series. Now on the AP test, the words or the phrase that you're going to see most often that tell you that this is the case is you'll see something like an alternating series with individual terms that decrease in absolute value to 0. And that is how we would verbalize that statement right there. And so they just give it to you in words instead of in symbols. But I need for you to recognize it in either case. Because if we have this, then we get this. Then all we have to do is take that positive, the positive portion of the alternating series and pop it into this limit. The one and only test if this is the case. We pop the positive portion of the alternating series and the limit as n approaches infinity. If we get 0 out of that limit, that series converges. What we're doing here, because every other term is not included in the sum, and remember for series, convergence means is the sum getting close to one value and staying there. We're not talking about what the terms are doing for series convergence. But what we're doing with these alternating series is we're going back to what's happening with the sequence. And it turns out that if we have this, then we're guaranteed, because every other term in the series is being subtracted from the accumulating sum, that when the sequence for large n converges, then the series will converge as well. So we're determining what the sequence is doing for large n. We only need to determine if the terms in the sequence are going to 0 as n tends toward infinity, because half the terms are being subtracted from the accumulating series sum. And then it turns out if the absolute value of the sequence terms does go to 0, the alternating series will, every single solitary time, be convergent. Now, here's the beauty part. Now again, we have to have the if. But if our terms, the absolute value of our terms, is going to 0, then we put that positive portion of the alternating series in this limit. If we don't get 0 out of that, then it diverges. There's really only one alternating series test, and it diverges. So pretty straightforward, pretty simple, but do not forget the if part of the statement that is required. So is the given series convergent or divergent? Well, the first thing that we need to do is determine if we're dealing with an alternating series, because if we're not, we're going to have to go pick up one of our positive series tests. So let's generate some terms and see if we have an alternating series. We're going to start with n equal 1. So the first term is negative 1 to the 1 times 1 plus 1 divided by 2. And that's all of that divided by 2. So this is 1 times 2, which is 2, divided by 2, which is 1. And this is, we could say that this is times 1 over 3 to the 1. So this first term is negative 1 over 3 to the 1, because this value is negative. Now the second term is negative 1. Now n equals 2. Oh, sorry, that's over 2. So that's 2 times 2 plus 1 divided by 2 all over 1, or sorry, times 1 all over 3 squared, where n equals 2. So we have 2 times 3, which is 6, divided by 2. Let's see, 2 plus 1 is 3, times 2 is 6, divided by 2 is 3. So that's a negative as well. So let's generate one more term and see what we've got. We have negative 1 to the 3, now n is 3, times 3 plus 1, and all of that is divided by 2, and that's times 1 over 3 cubed. So 3 plus 1 is 4, 3 times 4 is 12, divided by 2 is 6. This one is actually positive. This is 1 over 3 cubed. So now we're getting to where it looks like they're alternating. Well, does it matter that the first two terms were negative? No, because where does convergence or divergence happen? As n tends toward infinity. So we do absolutely have an alternating series here. I don't really need to generate any more terms. All I need to determine is that any one given term is bigger than the next term generated. If I can determine that, then I can run my series test. Well, it is true that 1/9, I'm taking this term right here, is greater than 1/27th, that term right there. So that is the case. I do have that going on, so that means I can use my alternating series test. Now, notice what I have here. Be really careful. This is important. This is where, students really tend to, they just tend to forget this after a while. I don't put the whole thing into the limit. I don't put the alternating term into the limit in the series test. I'll prove it. I'll go back here. Look, I just put the positive portion in the alternating series test. So I don't need that alternating term in this test at all. I need to determine the limit as n approaches infinity of 1 over 3 to the n. That's the positive portion, the positive counterpart to this alternating series. And sure enough, that goes to 0. So this series converges. I'm out of time on this video. Look for the next video.